Pressure beneath the Pacific does not announce itself with spectacle, yet the signals are there for those tracking the data. After a magnitude 7.5 earthquake struck Tonga on March 24, 2026, attention has turned sharply back to a region that only a few years ago produced one of the most powerful volcanic eruptions in modern history. How does a single seismic event connect to a much larger geologic system? Why are clusters of earthquakes appearing with increasing frequency in this part of the world? And could the same conditions that led to the Hunga Tonga Hunga Haapai eruption begin aligning once again? The earthquake itself was not just notable for its strength, but for the way its seismic energy traveled through the planet. Instruments recorded waves propagating across vast distances, circling the globe and returning as faint but measurable reflections. These global reverberations are not unusual for large earthquakes, yet their scale and clarity often depend on the structure of the Earth's interior and the energy released at the source. In this case, the signals were strong enough to register at the antipodal point, roughly 20,000 kilometers or about 12,400 miles away, near northern Africa, in a region that has also experienced recent seismic disturbances. The concept of antipodal seismic reflection is rooted in how waves move through the Earth's mantle and core. When a sufficiently powerful earthquake occurs, its energy radiates outward in all directions, bending and refracting as it encounters different layers of rock. Under the right conditions, some of that energy converges on the opposite side of the planet, concentrating stress in ways that can, in certain cases, contribute to additional seismic activity. While this does not guarantee another earthquake, historical patterns suggest that regions near these antipodal zones sometimes experience measurable responses within days or weeks. In recent months, parts of the Mediterranean basin have already shown signs of heightened seismicity. A deep earthquake measuring magnitude 6 occurred within Italy's broader tectonic environment, marking one of the strongest events in that region in nearly a decade. Greece and surrounding areas, long defined by complex fault systems and active volcanism, continue to register frequent low to moderate magnitude tremors. These developments, when viewed alongside the Tonga event, form part of a wider pattern that researchers have been tracking with increasing concern. Tonga itself sits along one of the most active subduction zones on Earth. Here, the Pacific Plate is forced beneath the Indo-Australian Plate at rates approaching 24 centimeters per year, or roughly 9.4 inches annually. This rapid convergence generates immense stress that accumulates over time and is periodically released through earthquakes and volcanic activity. Beneath the ocean surface lies a chain of submarine volcanoes, many of which remain only partially mapped, their structures hidden beneath several kilometers of water. Among these volcanic systems, Hunga Tonga Hunga Haapai stands out as a recent example of how quickly conditions can escalate. Beginning in late December 2021, activity intensified with intermittent explosions and ash emissions. By mid-January 2022, the system produced a massive eruption, estimated between volcanic explosivity index 5 and 6, placing it among the most powerful events recorded since Krakatoa in 1883. The explosion generated a shockwave that traveled around the globe multiple times, a tsunami that impacted coastlines across the Pacific, and an eruption column that reached heights exceeding 50 kilometers, or about 31 miles, penetrating deep into the stratosphere. Satellite observations from that period revealed extensive atmospheric disturbances. Volcanic lightning illuminated towering ash plumes, while pressure waves rippled outward in concentric patterns. Unlike many large eruptions dominated by sulfur dioxide emissions, this event injected an unusually high volume of water vapor into the upper atmosphere. Estimates suggest that tens of millions of tons of water were propelled into the stratosphere, altering its composition in ways that influence both short-term cooling effects and longer-term warming dynamics. That eruption did not occur in isolation. Seismic records leading up to January 2022 show increasing activity in the surrounding region, including clusters of moderate earthquakes and subtle ground deformation. These precursors, while not always definitive indicators, form part of a broader pattern often observed in subduction-related volcanic systems. The release of pressure along faults can alter stress fields, potentially affecting magma movement beneath nearby volcanoes. The events preceding the March 24th earthquake appear to follow a similar trajectory. In the week leading up to the magnitude 7.5 event, at least 3 earthquakes measuring magnitude 6 occurred north of Tonga, near Samoa. These were not random occurrences, but part of a sequence distributed along the plate boundary. When viewed collectively, they suggest a progressive release of energy across a wide region, rather than a single isolated rupture. Historical data reinforces this interpretation. Since 1980, the Tonga-Fiji-Samoa region has experienced a noticeable increase in both the frequency and magnitude of earthquakes. Early records show sporadic high-magnitude events separated by long intervals. More recent decades, however, reveal clustering periods where multiple large earthquakes occur within relatively short timeframes. Notable examples include a magnitude 8.2 earthquake in 2018 and a series of magnitude 7.2 to 7.6 events recorded in 2023. Cumulative seismic energy release charts, which track the total energy discharged by earthquakes over time, show an upward trend extending into 2025. This indicates not only more frequent earthquakes, but also a shift toward deeper and more powerful events. Deeper earthquakes, occurring at depths exceeding 300 kilometers, or about 186 miles, are particularly significant because they can influence stress distribution over much larger areas compared to shallow events. The connection between deep seismic activity and volcanic systems is complex. While not all earthquakes trigger eruptions, changes in stress and temperature conditions within the mantle can alter the behavior of magma reservoirs. In subduction zones, water carried down by the descending plate lowers the melting point of surrounding rock, generating magma that can rise toward the surface. Variations in stress can either facilitate or inhibit this movement, depending on the conditions within the crust. In the case of Tonga, the presence of multiple interconnected volcanic centers increases the potential for system-wide responses. Submarine volcanoes, in particular, can behave differently from their terrestrial counterparts. The pressure exerted by overlying water, often exceeding several hundred atmospheres at depths of 2 to 3 kilometers, or roughly 1.2 to 1.8 miles, can suppress explosive activity to a degree. However, when eruptions do occur, the interaction between magma and seawater can produce highly energetic explosions, as seen in 2022. The possibility of a repeat event, while uncertain, is being considered in light of these conditions. The March 24th earthquake released a substantial amount of energy, equivalent to several hundred megatons of TNT. Such a release does not dissipate instantly, but redistributes stress across the surrounding plate boundary. Areas that were already close to failure may now be closer to rupture, while volcanic systems may experience subtle shifts in their internal dynamics. Beyond the immediate region, the global context adds another layer of complexity. The Mediterranean, positioned near the antipodal zone of the Tonga earthquake, hosts several well-known volcanic systems. Mount Etna in Sicily, rising to over 3,300 meters, or about 10,800 feet, remains one of the most active volcanoes in Europe. Stromboli, often referred to as the lighthouse of the Mediterranean, exhibits near continuous eruptions, while the Santorini volcanic field in Greece has a history of large explosive events that have reshaped entire islands. These systems exist within a tectonic environment defined by the convergence of the African and Eurasian plates. The transfer of seismic energy from distant events, while not a direct cause of eruptions, can contribute to an already complex stress regime. Observations of increased microseismicity or ground deformation in such regions are often monitored closely following large global earthquakes. At the same time, broader environmental factors are being examined for their potential influence on geologic activity. The Earth's energy balance has shifted in recent decades due to a combination of increased solar absorption, greenhouse gas concentrations, and anthropogenic heat release. While these factors are primarily associated with climate processes, some studies suggest they may also interact with the lithosphere in indirect ways, such as through changes in sea level, ice mass distribution, and surface loading. Space weather, including variations in solar radiation and geomagnetic activity, is another area of ongoing research. Fluctuations in these external forces can induce electrical currents within the Earth's crust and mantle, though the extent to which they affect seismic or volcanic processes remains under investigation. What is clear is that the Earth operates as an interconnected system, where atmospheric, oceanic, and geologic components continuously exchange energy. The March 24th earthquake is a reminder of how quickly conditions can shift within this system. It did not occur in isolation, but as part of a sequence of events spanning multiple regions and scales. From deep within the mantle to the upper reaches of the atmosphere, the effects of such events propagate in ways that are still being mapped and understood. Monitoring efforts in Tonga and surrounding regions have intensified in response. Seismic networks, satellite observations, and ocean-based sensors are being used to track changes in real time. Data on ground deformation, gas emissions, and underwater activity are being analyzed for signs of further developments. While no single indicator can predict an eruption, the convergence of multiple signals often provides the most reliable assessment of changing conditions. The memory of January 2022 remains a significant reference point. That event demonstrated the capacity of a submarine volcanic system to produce global impacts within a matter of hours. It also highlighted gaps in monitoring capabilities, particularly in remote oceanic regions where instrumentation is sparse. Efforts to expand these networks are ongoing, but challenges remain due to the depth, distance, and technical complexity involved. As seismic activity continues across the Tonga Arc, attention is also focused on adjacent regions such as Vanuatu and the Solomon Islands. These regions share similar tectonic characteristics and have their own histories of large earthquakes and eruptions. Patterns observed in one area can sometimes provide insights into others, though each system retains its own unique properties. The question is not whether the Earth will continue to produce earthquakes and eruptions, but how these events will align in time and space. The clustering of seismic activity, the redistribution of stress, and the behavior of volcanic systems all point to a dynamic environment that is constantly evolving. The magnitude 7.5 earthquake has added another layer to this evolving picture, one that is being examined from multiple angles as new data becomes available. In the days and weeks following the event, subtle changes may offer clues. Variations in seismic wave patterns, shifts in ground elevation measured in centimeters or a few inches, and fluctuations in gas emissions from underwater vents are all part of the dataset being compiled. Each data point contributes to a broader understanding of how energy moves through the Earth's systems. Whether these signals will converge into a larger event remains uncertain. However, the combination of historical trends, recent activity, and the known behavior of subduction zone volcanoes ensures that this region will remain under close observation. The possibility of renewed volcanic activity, including an event comparable in scale to 2022, cannot be ruled out based on current patterns alone. In the immediate aftermath of the March 24th earthquake, attention has shifted from the release of seismic energy to the patterns that follow it. Earthquakes of this scale rarely act as isolated endpoints. Instead, they often mark transitions within a broader cycle of stress redistribution, where surrounding faults, volcanic systems, and deep structural boundaries adjust to a new balance. The Tonga region, already characterized by rapid plate convergence and complex undersea geology, is now being observed for these secondary changes with increasing precision. Seismic monitoring stations across the Pacific Basin have continued to register aftershock sequences extending both northward towards Samoa and southward along the Tonga Trench. While aftershocks are expected, their distribution provides insight into how stress has been transferred along the plate interface. In this case, the pattern is not confined to a single point, but appears stretched across hundreds of kilometers or several hundred miles, suggesting that the rupture influenced a broader section of the subduction zone than initially estimated. This type of distributed aftershock pattern can indicate that adjacent segments of the fault are being brought closer to failure. In practical terms, this does not mean that another large earthquake is imminent, but it does suggest that the region remains in a heightened state of mechanical adjustment. Small variations in stress, measured in fractions of a megapascal, can be enough to alter the timing of future events when systems are already near critical thresholds. At greater depths, seismic tomography data is being used to examine how energy from the earthquake propagated through the mantle. These imaging techniques, which rely on variations in seismic wave speeds, reveal zones of differing temperature and composition beneath the surface. In subduction zones like Tonga, descending slabs of oceanic crust can be traced to depths exceeding 600 kilometers, or about 370 miles. The interaction between these slabs and the surrounding mantle plays a key role in magma generation and volcanic activity. Changes in pressure and temperature conditions along these deep boundaries can influence how melt is produced and transported. When stress is redistributed by a major earthquake, it can subtly modify these conditions, potentially affecting the volume and movement of magma reservoirs. In most cases, these changes are gradual and may not lead to immediate surface activity. However, in systems that are already primed, even minor shifts can have observable consequences over time. Ocean-based instruments are also contributing critical data. Hydrophones, which detect sound waves traveling through seawater, have recorded low-frequency acoustic signals consistent with submarine volcanic activity in the broader region. These signals do not necessarily indicate an eruption, but they can point to magma movement, gas release, or small-scale explosions occurring beneath the ocean surface. Given that much of the Tonga volcanic arc remains submerged, such tools are essential for detecting changes that would otherwise go unnoticed. Satellite observations complement these measurements by providing a global perspective. Interferometric synthetic aperture radar, or INSAR, is being used to detect ground deformation with centimeter-level accuracy, equivalent to fractions of an inch. Even in remote oceanic regions, subtle bulging or subsidence of the ocean surface can sometimes be inferred through changes in wave patterns and sea surface anomalies. These techniques were instrumental in analyzing the precursors to the 2022 eruption and are now being applied again in near real time. One area of particular focus is the reformation of volcanic structures that were heavily altered during the previous eruption. The Hunga Tonga Hunga Haapai system experienced significant changes in its morphology, with much of the original island structure destroyed. Since then, satellite imagery has shown gradual rebuilding as material from the ocean floor accumulates and reshapes the volcanic edifice. This process is not merely surface level, it reflects ongoing magma supply from depth, indicating that the system remains active. The rate at which such structures rebuild can provide indirect evidence of magma movement beneath the surface. Faster accumulation may suggest increased supply, while periods of stagnation could indicate temporary declines in activity. Observations in the months leading up to the March earthquake showed intermittent changes, though not at levels that would have clearly signaled an impending large-scale eruption. The question now is whether the recent seismic event has altered this trajectory. Comparisons with historical events offer additional context. Large subduction zone earthquakes have, in some cases, preceded volcanic eruptions within the same arc. The mechanisms behind this relationship are still debated, but several processes have been proposed. These include stress transfer that can open pathways for magma ascent, changes in crustal permeability that allow gas to escape more readily, and shifts in hydrothermal systems that alter pressure conditions within volcanic conduits. However, these processes do not operate uniformly. Many large earthquakes occur without triggering eruptions, and many eruptions occur without preceding major earthquakes. The relationship is therefore probabilistic rather than deterministic. What makes the current situation notable is the combination of recent seismic clustering, the presence of an active submarine volcanic system with a history of large, explosive events, and the broader trend of increasing seismic energy release in the region. Stay informed as developments continue to emerge across the Pacific and beyond. If you found this report valuable, make sure to like, share, and subscribe for more in-depth coverage of global seismic and volcanic activity. Tap that hype icon to help this video reach a wider audience and keep critical updates visible to more people.